Hello dear students, I am Vara Prasad. I am discussing physics topic magnetism and matter for Neet students. So in the last two episodes we discussed what is a magnet, what is magnetic moment and a few problems on magnetic moment. Now in this episode, that is third episode, we shall discuss what is magnetic field, what are magnetic field lines, what are the properties of magnetic field lines. We know that if a small safety pin is placed closer to a magnet, then it gets attracted. That safety pin gets attracted strongly when it is placed close to it, and if it is taken farther from it, then the force with which it gets attracted with the magnet goes on decreasing. That means as we are taking it away and away, the influence of this magnet on this safety pin is decreasing. That means there is some space around the magnet where its influence can be felt. So at far away points, the influence of this magnet on the safety pin or any nail or magnetic material like iron, cobalt, nickel is very small. So the space around a magnet where its influence can be felt is called as magnetic field. So space around a magnet where its influence can be felt. Can be felt is called magnetic field. But nowadays this magnetic field can be defined from a mathematical relation that we know if a charged particle is moving in a magnetic field, it experiences force. The mathematical relation for that vectorially is given by F bar is equal to Q V bar cross B bar. Okay. So from this it is defined that if a charged particle moving in a region, moving at a point, experiences force because of its velocity and because of its charge, then we can say that there is magnetic field at that point. This is the modern way of definition of magnetic field. Now let us talk about what are magnetic field lines. So it is a visual representation of understanding the magnetic field that can be understood easily by a small experiment. That is, if a sheet of glass is placed over a magnet like this, and if iron filings are sprinkled over it, then these iron filings happen to be aligned in some pattern. They happen to be aligned like this. They happen to be aligned like this. So this pattern of the arrangement of these iron filings on the glass sheet on which this magnet is placed it enables us to understand the magnetic field lines. These magnetic field lines are imaginary lines. They can be drawn in different methods. The method of drawing it usually is that a bar magnet is placed first along geographical north-south directions. This is north, south, west, east. It is placed like this. The given bar magnet is placed like this, maybe with its south pole towards north or north pole towards south, doesn't really matter. So a small magnetic needle is placed, and that magnetic needle, if you place it closer to this north pole, let us say, the north pole of the magnetic needle happen to be, because it is repelled by it and attracted by it, is not, it is oriented like this. So the point where the tip of this north pole of the magnetic needle is pointing is marked. Then again this magnetic needle is placed in such a way that the south pole of the magnetic needle coincides with the point marked earlier. So again we get one more point. So that is how we can go on shifting this magnetic needle, and we can understand that the magnetic line of force is obtained like this. So that is, if this happened to be the bar magnet, then the magnetic field line, as we have drawn with the help of it, appears to diverge from north pole and converge into south pole. Similarly, on this side if I draw it, they are from north pole to south pole. But here we should understand one thing, that earlier I told you Ewing's theory of molecular magnetism. From that, whether a magnetic substance magnetized or not, every molecule of it is a magnet, and these molecules happen to be randomly oriented in case of an unmagnetized substance like a piece of iron that we see. But in case of a magnet, they happen to be oriented in an orderly manner. So because we cannot put this magnetic needle inside and try to draw them, so we can imagine that obviously the magnetic molecular magnets happen to be oriented like this. So we can understand that this is south pole, north pole. Why is it south pole? Why is it north pole? Already we discussed. In case of a magnet, there are so many molecular magnets. These happen to be arranged in an orderly manner. So here, from here to here, the effect of north poles are balanced by south poles, but this free end will be behaving like north pole because these effects of this molecular magnetic north poles are not balanced by anything. Similarly, this is north pole and this is south pole. So therefore, we can say that the magnetic field line is not just the curve drawn from north pole to south pole outside the magnet. Inside also we can imagine that it is extending from south pole to north pole. So we can say that these properties of magnetic field lines, if you have to talk about it, it is a closed loop. It is a closed loop. Outside the magnet, they are from north pole to south pole, but inside the magnet, they are from south pole to north pole. They are unlike the electric field lines. In case of electric field lines, they are open curves. We shall see the comparison after a little more time. But first, we shall concentrate on the properties of magnetic field lines. First property of magnetic field line is that they are closed loops. From north to south outside the magnet. And from south to north inside the magnet. Now, second one, if I say, that is a very important one. Actually, we have got this, the magnetic field line by seeing the direction in which this north pole is oriented. Therefore, tangent drawn to a magnetic field line at any point gives us the direction of the magnetic field. That is, for example, if you want to find the magnetic field, direction of the magnetic field here, you just draw a tangent. This tangent indicates the direction of the magnetic field at that point. So, tangent drawn to a magnetic field line at a point gives direction of magnetic field at that point. So, from this we can understand one thing, that magnetic field lines do not intersect with each other. The third property is that they do not intersect with each other. Why don't they intersect with each other? For example, if it is the point of intersection. At the point of intersection, we can draw two tangents, one tangent like this, one tangent like this. But magnetic field being a vector, it has only one direction. So this is indicating point of intersection. At the point of intersection, two directions are possible. Therefore, it is impossible. Hence, we can say two magnetic field lines do not intersect with each other. It is the third one that I have to talk about. And then fourth property, what it indicates is they try to contract lengthwise. See here, had it not, it is not going this way and coming back, rather the lengthwise it is trying to contract, which is due to the fact that the unlike poles attract each other. Okay, so they contract lengthwise. It is due to attractive force, attraction of unlike poles. Now, we shall see the magnetic field lines due to a bar magnet, due to a solenoid, and due to an electric dipole, so that we can talk about one important comparison. For example, if this is a bar magnet, as we have been talking about it, this is a north pole, this is south pole. So, as we discussed, the magnetic field lines outside the magnet happen to be from north pole to south pole outside the magnet. They are not. Okay. So, if you see here, actually they are in the magnet, they are like this. If I say this is this in the magnet. In the magnet, they are from south to north. So, here if you see a small closed surface, let us say Gaussian surface, here in this, if you see a small Gaussian surface there, and if you see a small Gaussian surface here, so the magnetic field lines happen to be crowded here and the magnetic field lines are less crowded here. So, magnetic field lines, if they are crowded more, it indicates that the magnetic induction or the magnetic field strength is more. If you see, this is the closed region, there they are crowded more, here they are crowded less. So, the region where the magnetic field lines are crowded more indicates the magnetic field is stronger there compared to the regions there. For example, if you consider this as region 1 and this is region 2, so magnetic field, strength of the magnetic field is more at region 1 than at region 2. So, from this we can say, this is what we observed. From this we can say that fifth property, the magnetic field lines crowded at a point indicates the magnetic field is stronger compared to the points where they are less crowded. Then, so let us look at even the electric line of force. If it is an electric dipole is one, already we discussed in the previous topics, that if it is a positive charge, it is a negative charge, two equal and unlike charges happen to be separated by some distance, then we call it as an electric dipole. Let us say it is this. The electric line of force, they diverge from north pole and they diverge from positive charge, and they converge into south. So, here they happen to be like this. You do not see the electric line of force inside this charged body. They exist only outside it. So here they are like this. So the very difference between the electric line of force and the magnetic field lines is that here magnetic field lines are closed curves. So if you observe, they are like this, they are closed curves, whereas electric field lines, they are diverging from positive charge, converging on negative charge, but they do not exist inside the charged body. They do not exist inside it. So this is the basic difference between electric field lines and magnetic field lines. Now there is one more thing that we have to talk about as magnetic field lines. So if you draw the magnetic field lines in a ferromagnetic material, then field lines are found to be converged. For example, let us say this is some magnetic field in some region represented by the magnetic field lines. In that region, if I place a ferromagnetic material, let us say we have placed a ring made up of iron or cobalt, etc. Now earlier, if the magnetic field lines were like this, now what happens is we can say the magnetic field lines, they try to converge through this. All these magnetic field lines are trying to pass through this. That is, magnetic field lines, they pass through this ferromagnetic material, they try to crowd through this ferromagnetic material. This property can also be made use for safeguarding these sensitive instruments. Like if you want to see that the watch parts, if they are to be safeguarded from the external magnetic field, then an iron ring is placed over them. An iron ring is placed around the sensitive parts so that they can be safeguarded. Okay? So these are the properties of magnetic field lines. Now once we understand what is magnetic field lines, now we shall talk about the next one, that is magnetic field, magnetic induction. Now let us discuss the force between magnetic poles. Though the magnetic poles do not exist as monopoles, Coulomb, he gave an empirical relation for finding the force between two magnetic poles, which is known as Coulomb's inverse square law. So Coulomb's inverse square law says that if this is a magnetic pole of pole strength m1 and this is another magnetic pole of pole strength m2, then, and if they are separated by a distance r in air, the force between these two magnetic poles is directly proportional to the product of their magnetic pole strengths and is inversely proportional to square of the distance between the two poles. So from this we can say that F is equal to some constant C into m1 m2 over r square. So this constant of proportionality is found to be dependent on the medium between the two magnetic poles, and its numerical value is found to be dependent on the measurement of the system of measurements. That is, in SI, if the medium is A in SI system, the constant of proportionality is found to be mu naught by 4 pi. This mu naught is called permeability of the vacuum or free space. This permeability of vacuum or free space is equal to 4 pi into 10 to the power of minus 7 Henry per meter or Newton per ampere square. The dimensions are the units, we can get it from this. Here C is Fr square by m1 m2. Here m1 and m2 are measured in ampere meter, therefore it is Newton meter square by ampere square meter square, hence it becomes Newton per ampere square. But Henry, this unit will come across later in a topic electromagnetic induction. Now therefore, force between two magnetic poles separated by a distance r in air is obtained by F is equal to mu naught by 4 pi into m1 m2 by r square. And as I told you already that this constant of proportionality also depends upon the medium, we can say if medium is other than air or vacuum, then in SI, this F is given by, it is mu by 4 pi into m1 m2 by r square, where this mu is called permeability, absolute permeability of the medium, absolute permeability of medium. This can be written as mu naught times mu r, where mu naught is the permeability of vacuum, mu r is the relative permeability of the medium. So this expression, instead of writing F is equal to mu by 4 pi m1 m2 by r square, we can write even this as mu naught times mu r by 4 pi into m1 m2 by r square. Now we shall see one or two problems based on this. Let us discuss one or two problems on this Coulomb's inverse square law. Let us say two magnetic poles of pole strengths m1 and m2, they are such that the magnetic pole strength of one is 4 times the magnetic pole strength of the other, are separated by a distance of 10 centimeter in air, so that the force experienced by each magnetic pole due to the other happen to be 10 milligram weight, okay, where G is 10 meter per second square if I take. Then find the pole strength of the stronger pole if it is asked. We know from Coulomb's inverse square law, F is equal to, if the two magnetic poles happen to be separated in air, mu naught by 4 pi m1 m2 by r square. So we can write this F is equal to, F already we got it as 10 milligram weight, 10 milligram is 10 to the power of minus 3 milligram is 10 to the power of minus 3 kg, therefore it is 10 to the power of minus 6 kg times 10, because it is force is mg. So it is 10 milligram stands for 10 to the power 10 into 10 to the power of minus 6 kg, and g is 10, is equal to 4 pi mu naught by 4 pi happen to be 10 to the power of minus 7. Already we learned that mu naught is equal to 4 pi into 10 to the power of minus 7 SI units, and m1 and m2 happen to be 4 m1 square, because m2 is 4 m1, and they are separated by 10 centimeter air, so therefore 10 to the power of minus 2. 10 centimeter is 0.1 meter, whole square is 10 to the power of minus 2. And from this we can get 4 m1 square is equal to, it is 10 to the power of minus 4, 10 to the power of minus 6 divided by 10 to the power of minus 7. So therefore it is 10 to the power of minus 4, 10 to the power of minus 6 divided by 10 to the power of minus 7 is 10 by 4, it is 2.5. So we get it to be m1 square to be equal to 25 by 40. Hence m1 can be written as 5 by 2 root 10. This on simplification we get it to be, just we shall put it as it is. And if you want to find the magnetic pole strength of the stronger pole, which is m2 is equal to 4 m1, that happen to be, it is 4 times 5 by 2 root 10 ampere meter, that happen to be 10 over root 10, that is nothing but root 10 ampere meter. Now, we shall discuss another problem on this Coulomb's inverse square law. Let us say this is an equilateral triangle ABC of side A. At these two vertices, if two identical poles, that is of same pole strength and same polarity, if they are placed, force between them is found to be F. This is a pole of pole strength M, this is a pole of pole strength M. Let us say this is north pole, this is also north pole from the data. So they repel each other, so force on this by this, force on this by this, they are of equal magnitude, because force between two magnetic poles obeys Newton's third law. So this is F by magnitude, this is F by magnitude, but they are opposite in direction. So that F by magnitude is mu naught by 4 pi into m square over a square. Now, if a third identical pole, this is what is data given. If a third identical pole, if third pole of same strength but of unlike polarity is placed at the third vertex, that is at vertex A pole of pole strength M is placed but of unlike polarity. If these are north poles each, then we have to say it is south pole. Now, this south pole, what is the force on this south pole? That is the question. We know that this south pole is attracted by this north pole. This south pole is also attracted by the north pole. So if I call it as F1 and F2, these F1 and F2 are of equal magnitude, which can be given by again the expression mu naught by 4 pi, and the pole strengths are same, hence m1 times m2 is m square over a square. So it is same as what is given as F from equation 1, that is F1 and F2 is also equal to F, but they happen to be acting at an angle 60 degrees. If two equal magnitude vectors are acting at an angle theta between them, then magnitude of the resultant we can find it using the expression 2f cos of theta by 2. Therefore, it is 2f cos 60 by 2 is cos 30 degrees, cos 30 is root 3 by 2. So therefore, net force experienced by the unlike pole of same polarity, say unlike pole of same magnitude, same magnetic pole strength placed at third vertex is given by root 3 times F.